All right, so you've done all the hard work. You've trained a regression model, and it's spitting out predictions. But, and this is the big question, right? Are those predictions actually any good? Let's dive in and figure out how to answer that with some real confidence. Getting a prediction is really just the first step. It's kind of like a detective finding a clue at a crime scene. That clue is totally useless until you know what it means. We've got to evaluate our model to see if it's, a brilliant detective or if it's just making wild guesses. Yeah, just making predictions isn't going to cut it. We have to be able to quantify the quality of those predictions. Without evaluation, we're basically flying blind. We have no idea if our model is truly getting the patterns in the data or if it's just, completely off the mark. And that's exactly where evaluation metrics come in. Think of them as tools that give us an objective score for our model's performance. They turn that fuzzy, vague question of, is it good, into a hard number we can actually use to judge our work and, more importantly, make it better. So let's open up our Detective's Toolkit for investigating model performance. Today, we're going to look at 4 of the most essential tools for any regression task. And what's cool is that each one tells us something just a little bit different about where our model is going wrong. First up, we've got mean absolute error, or MAE. This is your trusty, no-nonsense tape measure. It tells you, on average, how far off your predictions are. Super simple. If your MAE is 5, it just means your predictions are, on average, 5 units away from the real value. It's intuitive, it's easy to explain, and it's a fantastic starting point. Next in the kit is mean squared error, or MSE. Now, the keyword here is squared. By squaring the errors, MSE puts this huge penalty on large mistakes. So an error of 10 becomes 100, but an error of 2 only becomes 4. This makes MSE really sensitive to those big outlier predictions. And because of that, it's incredibly useful when you're training a model, because it really forces the model to avoid making those big, embarrassing mistakes. Okay, so MSE is great for training, but its units are weird. They're squared. Like, dollars squared? What even is that? It doesn't make a lot of sense. So we just take the square root of it to get the root mean squared error, or RMSE. And bam! This translates the error right back into the original units you care about. It's our practical field report, telling us our model is off by, say, 0.35 centimeters on average. So much easier to understand. And finally, the grand finale, R squared. Think of this one as the final case summary. It answers the big question. How much of the mystery did our model actually solve? It does this by measuring how much of the variance, which is just a fancy word for how spread out or chaotic your data is, our model can explain. An R squared of 0.85 means your model explains 85% of that spread. That's way, way better than a dumb model that just guesses the average every single time. That one would get an R squared of 0. So, let's do a super quick recap. You want to use MAE for a simple, solid error measure. Use MSE during training to really punish those big mistakes. Use RMSE to talk about the model's average error in real-world units. And use R-squared to see just how much better your model is than a simple guess. Got it? Good. Okay, theory is great and all, but let's see these metrics in the wild. We're going to grab the famous IRIS dataset and really put these tools to the test. So we've built a pretty simple linear regression model. Its only job is to predict the length of a flower's sepal based on its other features. The model has done its work, it's made its predictions, and now it's time to bring in our detective kit and see how it did. And the first piece of evidence is in, an R-squared score of 0.85. This is awesome! It tells us our model can explain about 85% of the variance in sepal length. That is so much better than a baseline model, which, remember, would have a score of 0. We are definitely onto something here. Now check this out. Our model's RMSE is about 0.35 centimeters. That means, on average, its predictions are off by just that much. But a really basic model that just guesses the average sepal length every time, it would be off by around 0.82 centimeters. Our model literally cut the error by more than half. That is a huge, undeniable win. But listen, a truly great detective knows the numbers. The scores are only part of the story. To really understand our model, we need to look at the evidence it left behind. We need to look at the errors themselves. This right here, this is a habit that separates the pros from the amateurs. The scores look pretty good. I mean, yeah. But are there hidden patterns? Is our model systematically biased in some way? Maybe it's great at predicting for small flowers, but absolutely terrible for large ones. These single number scores, they just can't tell us any of that. To find out, we look at the residuals. A residual is just the error for a single prediction. It's the actual value minus whatever our model predicted. You got to think of these like the fingerprints left at the scene of each and every prediction. They hold all the hidden clues. And here it is, the smoking gun. When you actually plot these residuals, what you want to see is a random, shapeless cloud of dots centered around the zero line. That means you have a good fit. But if you see a pattern, like a U-shape or a funnel where the errors get bigger and bigger, that's a massive red flag. It's screaming at you that your model has a hidden bias and is failing in a predictable way. So, we have all these tools in our belt: MAE, MSE, RMSE, R-squared, and of course, residual plots. How in the world do you choose which one to focus on? Let's wrap all this up with some clear, practical advice. Here it is, your detective's cheat sheet. If you're training a model and you want to really punish big errors, look at MSE. If you want to explain the average error in a way that anyone can understand, use RMSE or MAE. To brag about how much better your model is than just guessing, use R-squared. And most importantly, if you want to find the hidden story and the secret flaws in your model, you always look at your residual plots. And that really is the heart of it, isn't it? The metrics give you a score. They give you a grade for your model's performance. They tell you if it's good. But analyzing the residuals, that's what tells you the full story. It tells you why it's good or why it's bad and exactly where it's going wrong. So the next time you build a model, please don't just stop at the R-squared or the RMSE. Go that one extra step. Ask yourself, my model has a score, but what story are its errors telling me? The answer to that question will make you a much better data scientist.